Welcome back everybody. Today we'll again continue with the chapter Kinetic Theory of Gases, and we'll be studying the degree of freedom, law of equipartition of energy, and calculation of the molar specific heat capacities of gases. Degrees of freedom of a system are defined as the total number of coordinates or independent quantities required to describe completely the position and configuration of the system. It can also be defined as the number of ways in which the particles can absorb energy. So the general formula for the degrees of freedom can be given as F is equal to 3n minus k, where n is the number of particles in the system and k is the number of independent relations between the particles. The degree of freedom for a monoatomic gas is 3, as a monoatomic gas has a single atom or a point mass and is capable of having only translatory motion. For a diatomic gas like nitrogen, oxygen, hydrogen, carbon monoxide, etc., there are 3 degrees of motion corresponding to the translatory motion, and there are 2 additional degrees of freedom due to rotational motion. So the total degrees of freedom is 5 for a diatomic gas, while for a triatomic or polyatomic gas, the number of degrees of freedom for non-linear molecules is 6. The law of equipartition of energy states that for any system in thermal equilibrium, the energy is equally distributed amongst its various degrees of freedom, and the energy associated with each degree of freedom per molecule is 1 by 2 kT, where K is the Boltzmann constant and T is the absolute temperature of the system. So as per the equipartition of energy, the total energy of monoatomic gas will be 3 by 2 kT, for diatomic 5 by 2 kT, and for a polyatomic gas it will be 3 kT. Using the law of equipartition of energy, we can calculate the value of molar specific heat of gas at constant pressure, constant volume, and gamma, which is defined as the ratio of the molar specific heat at constant pressure to that at constant volume. Now let us see how to calculate Cp and Cv, that is the molar specific heat at constant pressure and volume respectively, for a monoatomic gas. Now the energy associated with a monoatomic gas, as it has 3 degrees of freedom, is 3 by 2 kT. For 1 mole of such gas, the total internal energy, which is equal to the total kinetic energy for an ideal gas, will be equal to 3 by 2 RT for 1 mole of gas. Now, the molar specific heat at constant volume is equal to the du by dt, where u is the total internal energy, and it comes out as 3 by 2 R. Cp minus Cv is R. So substituting the value of Cv as 3 by 2 R, we get Cp as 5 by 2 R. And the gamma, which is atomicity, is equal to Cp upon Cv, which is 5 by 3 for a monoatomic gas, which is equal to 1.67. So for every monoatomic gas like helium-argon, gamma, or the atomicity, is 1.67. Similarly, we can calculate Cp and Cv and gamma for diatomic and polyatomic or triatomic gases also. For diatomic gases, the value of gamma is 9/7, which is 1.28, and for triatomic gas, it is 1.33. The root mean square or RMS speed of gas molecules is defined as the square root of the mean of the squares of speed of all the gas molecules. It is denoted as VRMS and it is equal to square root of V1 square plus V2 square plus V3 square plus so on up to Vn square divided by n, where V1, V2, V3 and so on up to n is the speed of the n molecules of the gas. Now we know that the pressure P is equal to 1/3 rho V square. So VRMS will be equal to under root of 3P upon rho, which is also equal to square root of 3kT upon m, where m, if we consider for 1 mole of gas, will be the molecular mass. So from here we can calculate the RMS speed of air and hydrogen molecules at normal pressure. For air, the RMS speed is 485 meters per second, and for hydrogen, whose density is 0.09 kg per meter cube, the RMS speed is 1835 meters per second. Mean free path. Now the molecules of a gas are in a state of continuous random motion. As these molecules have a finite though small size, they always collide against one another frequently. So the distance between two successive collisions, the molecule will move along a straight line path with a uniform velocity, and this free path is known as the mean free path. It is equal to kT upon 2 pi d square rho, the square root of this term. So from here we can see that lambda, or the mean free path, is inversely proportional to the density of the gas. It is directly proportional to the mass of the gas molecule. It's inversely proportional to the square of the molecular diameter, directly proportional to the absolute temperature, and inversely proportional to the pressure of the gas.